Do you guys still see the slide?
Yes.
Okay, then let's start. Good afternoon, everyone, or good evening, or good night, depending where you are. My name is Aydar Akçurian, and I would like to welcome you on behalf of TriboNet team today. Welcome and thank you very much for being with us today, and I'm pleased to have with us Dr. Vladislav Yastrebov. The topic of the seminar, or the webinar, is the contact of rough surfaces and their sealing performance. Before we start, I would like to take a moment and thank the sponsor of today's webinar, Artec Instruments. Artec Instruments provide single function and multifunction tribometers that characterize friction, wear, adhesion, fatigue, and several mechanical properties under vacuum, high pressure, high temperature, cryo, and standard environmental conditions. Artec Instruments also provide testing solutions for surface, such as scratch testers, instrumented indentation, twin and three rollers, fretting, and 3D optical profilometry for characterization and inspection. Please feel free to visit their website and find out more information on various solutions in tribology and lubrication fields. I would also like to thank our media partners, Society of Tribologists and Lubrication Engineers, STLE, for co-organizing this event. STLE is the technical society serving the needs of individuals, but also organizations that comprise the tribology and lubrication engineering business sector. You can become a member of STLE and enjoy the benefits of it. So please take a look at their website for further details. And now back to the show. A quick plan for today. We have 45 minutes of the presentation followed by a Q&A session. During the talk, the microphones will be muted to make it easier for the presenter, but you can write your questions in the chat during the presentation and afterwards, and we will unmute you and you will get the opportunity to ask your questions if the time permits, of course. And now let me shortly introduce Dr. Vladislav Yastrebov for those of you who might not know him yet. Dr. Vladislav Yastrebov earned bachelor's and master's degrees in applied mechanics at St. Petersburg Polytechnic University in Russia. Over the final years of his studies, he worked as an engineer in research and department, modeling and simulation department at Corning Research Center of Corning Incorporation. In 2007, Vladislav moved to France to start his PhD studies on computational contact mechanics at Center for Materials Research Laboratory of Mainz Paris Tech. At the same time, he took a part in a research project on metal-to-metal sealing at the roughness scale of the secondary water cycle valves of nuclear power plants. His PhD thesis, Computational Contact Mechanics, Detection, Geometry and Resolution Techniques, earned him several awards, and after being slightly extended, was published as a book, Numerical Methods in Contact Mechanics by Willy, IST in 2013. After two postdocs on the origin of friction at EPFL, Switzerland, in Professor Molinari's group, and on dislocation dynamics in France, Vladislav got a tenured CERS research scientist position at the Center for Materials Research in October 2013. There he continued his research on various aspects of contact and friction between materials. Dr. Yastrebov has an expertise in micromechanical contact modeling, surface roughness, and frictional instabilities. Now, his research activity spans such topics as electrical contact, basal sliding of glaciers and iceberg glacier interaction, metal-to-metal sealing engineering, coupled fluid-solid and thermomechanics in contact interfaces, wear of drilling tools, tire grip, wear tools, micromechanical modeling of cemented tungsten carbides, and development of advanced numerical methods to treat contact and friction in the framework of finite and boundary element methods. For this work, Dr. Yastrebov was awarded a CNRS Bronze Medal 2018, the highest distinction for early career scientists in France. Without further ado, Vladislav, the floor is yours, and I'm looking forward for your talk.
Yes, thank you very much, Haidar, for this very nice and long presentation. And thank you, Manoj, for all the organization. Good morning and good afternoon for everybody. That's a great pleasure for me to present you some research results. I hope that now you can see my screen. Right? Could you please confirm?
I cannot see it yet.
Wait. Strange. Let me refresh it again. Okay, now should be fine.
Yeah. Yes, I think it's coming.
Yes, right, you can see it.
Yes, we can see it.
Okay, thanks. So the topic is contact of rough surfaces and its sealing performance. So there will be three parts: about roughness, about contact, and about sealing. And of course, it's a joint work which was done with Andrei Schwartz, now at Glasgow University, Guillaume Ancieux and Jean-François Molinari at EPFL, and my ex-colleague Georges Caïton, who has retired now. And well, I worked on in this domain for 15 years already, and all the results it's also the results of interaction and collaboration with many other people like Julien Durand, Paul Bigan, and many others. So thank you for being here. I hope you'll enjoy the talk. But first of all, I would like to say one word. Today it's February 24th, and it's the day of the war onset in Ukraine, and I would like to express my position about this stuff. I stand with Ukraine in this conflict, so unfortunately it lasts already for 1 year. Would be happy that it stops as soon as possible. Okay, now going back to the scientific presentation, just 2 words about myself, but Eidar has already presented most of my research domains, and indeed I work on some overlap, intersection between mechanics of materials, numerical methods, some geophysics, some tribology, some contact mechanics and solid mechanics and fluid mechanics and so on. So here's the research topics on which I work. And today I will be happy to present you some results on the mechanics of contact of rough surfaces and also on metal to metal, or just rough on rough sealing performance of the contact interfaces. Okay, the outline of the presentation is very simple. First part will be about surface roughness, how to characterize it, and which characteristics will be important for the following sections. Section 2, it's about mechanical normal contact of rough surfaces, how to actually evolve, how to model the evolution of the true contact area and the gap in the contact interfaces with applied pressure. And the third part, the last one, it's about interfacial fluid flow under 2 rough surfaces squeezed together by external pressure. And I will try to address 2 questions: how the true contact area, which is central for many tribological problems, how this true contact area evolves under increasing pressure and which parameters influence this evolution. And the second question is how the roughness affects actually the permeability of transmissivity of the contact interfaces. Here's the problem. The first problem I solve this contact between a rigid flat and an elastic solid, and the second problem will be how the fluid can go through the interface. That's the simple outline of the presentation. And before I start, I'd just like to show this figure describing the complexity of what happens in the contact interfaces. This is very interesting from scientific point domain, from scientific point of view domain, and very challenging from engineering one, because scientists just like to understand what happens, and engineers need to understand it. So in this short presentation, I will focus rather on a very simple part. It will be normal contact between elastic rough half spaces squeezed together with some saturated lubricant or fluid in the interface. That will be the topic of the presentation. So let's start with the description of the surface roughness. First of all, there are different kinds of roughness, right? The roughness which we can see with a naked eye, like asphalt concrete roughness or fracture surface in rocks, in stones. This kind of roughness is important for some applications like shale gas, oil and gas extraction, tie rod grip, and so on. But there is a more subtle roughness, the roughness of metallic surfaces, which we hardly can see with naked eye in most cases, right? And this roughness, even though it's small, it seems to be small, it affects all the interface physics. Oh, that's okay. Can you still hear me? I'm not sure because and can you still see my slides?
Yes, we can see everything. Yeah.
But is there a delay between what I show and what I say? No, it's fine.
No, it's all good. Yeah.
Okay, thank you. Sorry for. Okay, so this roughness is important for many applications in tribology, and notably for metal seals, for piston liner contact, and many other applications. So, how to characterize this roughness? First of all, to simplify the story, we'll assume that the roughness could be given by this equation z out of plane coordinate as a function of x and y in plane coordinates, right? I can distinguish two families of parameters. The first one, parameters of surface roughness, which are independent or weakly dependent on the sampling, on the resolution with which we measure the surface roughness, or delta x. The first such characteristics is RMS roughness, or SQ, simply root mean squared roughness, this parameter, which is very weakly dependent on the scale and on the sampling step. The second parameter, which is important, it's a power law decay. If there is a power law decay for the power spectral density phi, right, then we can characterize this decay with an exponent dependent on h, and this characteristics is kind of resolution independent. Okay, those are two simple parameters, but there are many other parameters which are unfortunately sampling dependent, resolution dependent, and the first one is root mean squared gradient of the surface roughness, SDQ, this one. And there is another one, if we can go to any order, is root mean squared curvature, SDDQ. Okay. But we won't use SDDQ as it is in our developments. We'll use another parameter which is called Nayak parameter, which is a combination of 0, 4th, and 2nd spectral moments, or can be given by this equation. Okay, it's a combination of SQ, SDQ, and SDDQ. All right. So here I show you a few examples of model surface roughness, which is Gaussian, isotropic, and self-affine. Self-affine, I mean, it has specific power law decay for the power spectral density. So yeah, just We use this model roughness to study the effect of different parameters on the tribological properties of the contact interfaces. Okay, this is a idealized world where we can model roughness. In reality, roughness could be much more complicated than this. And for example, this is an example of asphalt concrete roughness. Here is the scale 20 by 10 centimeters. And at this scale, for example, this asphalt concrete has not at all Gaussian, absolutely non-Gaussian height distribution. So here is height, here's PDF probability density function, which can be described by generalized variable function. But if you zoom close enough in the surface roughness, you'll see different things, a different magnification, and in a very small scale, the roughness, even though it's not isotropic, but at least its high distribution could be characterized as Gaussian one. So this is an example of surface roughness which is hard to characterize with classical simple models. A few more comments about surface roughness. Often when we deal with experimental data, we obtain quite coarse representation of surface roughness. And here is an example. It's a metallic surface with the sampling of approximately 1 micrometer. And on the left, you can see experimental data that we have. If you go along a profile, every second or every third point would be peak. Okay. So with this surface roughness, we cannot really do numerical modeling because we cannot ensure mesh conversions. We do not know what happens on the smaller scales. So therefore, when we deal with this kind of roughness, we enhance the surface roughness with a smoother surface between experimental data points. That's what I show on the right. One more comment about the power spectral density, which is frequently used in, at least in my research domain. The power spectral density, defined by capital phi, it doesn't distinguish between z and minus z. Therefore, the power spectral density of this surface and this one would be the same. However, you can imagine that mechanical contact between this surface and flat one and this one would be really different. So therefore, we need to pay attention when the height distribution is not symmetric. We need to use power spectral density with caution. Along with this observation, you know that even though surface roughness, initial surface roughness could be Gaussian after some run-in or some plastic deformation on the highest asperities, or because of where the right tail in the high distribution could be removed, and we obtain a surface with a negative skewness, so which is non-symmetric. Therefore, for this kind of surfaces, the power spectral density approach and all the spectral moments cannot be really used. And here's this example of this asphalt concrete, which is not Gaussian. Okay, that's it. Now we can characterize roughness. We understand the risks of non-symmetric Gaussian surface, non-Gaussian surface. And now let's try to solve a mechanical problem. The problem is the following. We have to solid which come in contact, well, which are made of different materials, elastic materials to start with, and every solid has its own roughness, Z1 and Z2. Okay, we squeeze them together by external pressure PO, and we are interested in what happens in the interface between these two rough surfaces. Here's the illustration. In equations, it looks like this. So we solve the balance of momentum, and in the interface, we plan to fulfill contact constraints. So there is no penetration, and the pressure is always positive, non-negative. Okay, this problem cannot be solved easily at all, we can say, using analytical methods, and we can rather use numerical methods, either the finite element one or the boundary element method, the classical one, or the spectral version of it. But of course, there are some analytical models which are constructed on some assumptions. The first family of analytical models are multi-asperative models, which represent the surface roughness by a set of asperities. Yeah, we can detect on the surface roughness asperities, characterize their principal curvature, and use either geometrical average or algebraic average if you want to solve simple conic problem for the slowness of revolution, or we can use these ellipses as they are in BGT theory. So I guess everybody knows about these approaches. So here I just show two examples of surface roughness with small spectral content and rich spectral content, and all the asperities detected on this surface roughness. Okay, lately we can use the information about high distribution of asperities, and we use simply a Hurst theory for the penetration or for the overlap given by delta. We can find the force, and we can find the contact radius for every asperity in a statistical sense, and by integrating all of them, we can obtain how the contact area evolves with the total force, right? However, the assumption of most of these multi-asperative models that this induced surface deformation, which has to be there, is not taken into account. So this out of plane deformation is ignored in multi-asperative models. Okay, the second family was developed by Bo Person. I guess most of you heard about this one. He developed this diffusion equation for the probability density of interface pressure, how it evolves with the second spectral moment, which I have already introduced. But okay, I have no time to enter into details of his theory. I would rather show you the results, the predictions of these two families of models. Both models predict the linear evolution of the true contact area, normalized by the nominal one, with the applied pressure PO. So your pressure, you can see it's normalized by effective elastic modulus E star, and here in the denominator we have a RMS gradient of roughness, or SDQ. However, the proportionality coefficient, proportionality factor K, is different. In multi-asperative models, is approximately 2.5 and 1.6 in Person's model. But the evolution for the contact area, which tends to 0 for infinitesimal contact area, they both predict linearity. Okay. However, if we are interested in a high contact area, like 5–10% or even more, then multi-asperative models, all multi-asperative models, they have a strong dependence of the evolution on Nayak parameter alpha that I have introduced earlier. But in Person's model, there is no such dependence, and the entire evolution of the contact area can be predicted as an error function of this normalized pressure, and only one parameter is needed in SDQ, or RMS gradient of roughness. So now on our side, we tried to solve this problem numerically as accurately as we could. First of all, in order to solve this problem, we mapped this to a simpler one where the contact occurs between an effective roughness, which is a combination of two surface roughnesses, and a flat elastic half plane, half space, sorry, with effective elastic modulus. And the problem of contact could be formulated as optimization problem to minimize some functional complementary energy under some constraints. Constraint that the pressure is everywhere non-negative, and that the average pressure is given to the applied pressure. Okay, so what we did a lot of different simulations for surfaces with different cutoffs. When I say cutoff, I mean the longest wavelength in the surface spectrum and the shortest wavelength were controlled by ourselves. So we control the Hurst exponent, or the fractal dimension, of our generated model surface roughness. And for every combination of all these parameters, we generated 10 random surface realizations to get some statistically meaningful data. The discretization was about 2000 by 2000 points on the surface. And we did a simulation from zero contact to full contact. Here how it looks like the evolution of the contact area for two systems. The first one, it has a longest wavelength in the spectrum equal to the period of our simulation domain. So it's a spectral method we use. So it means that the solution is periodic, and the longest wavelength is equal to this period. However, the shortest wavelength is 32 times shorter. Okay, 32. Here, the shortest wavelength is the same. However, the longest one is 16 times shorter. So this surface is Gaussian, and this one is not. But the evolution, I will show you later the evolution, it's very similar. However, the morphology of the contact spots is very different. So I increase the pressure, and we see that the contact area occupies more and more space. At some point, what you can see, so here there is no yet infinite cluster. It means that the fluid can pass, if there is would be fluid passing through the interface, it can pass from lower side to the upper side. And here as well, you can find the path from lower side to the upper side. However, if you increase slightly more the external pressure, we will close all the possible passage paths, and it means that we form an infinite cluster and we reach the percolation limit. Okay, so we can charge more, squeeze more, and go to the full contact. So here the summary of the results. On the x-axis is normalized pressure, y-axis is the true contact area fraction. And you can see all our results for all different cutoffs, all different parameters are here. So these color lines, slightly above Pearson's model, but in the limit of small contact area, we tend closer to the multi-aspirity asymptotic solution. Okay. But in reality, for most applications, the region of interest is here. In many applications, we don't go for very high contact area. So let's zoom in and see what is going on here. So now you can see some difference between all our results. And what we can remark that for higher Nayak parameter alpha, we get smaller and smaller contact area A, okay, for a given pressure. It took us some years to get such accurate results, because as we demonstrated, even a small error in simulations, in discretization, even though we use relatively fine discretizations, small error in discretization could affect significantly the results. And I won't present in detail, but we developed a very simple formula equation which allowed us to estimate the true contact area A star through the simulated contact area and the computation of the discrete perimeter, all the passages transition from contact to non-contact, SD. So knowing simulated area and SD perimeter, we can obtain very accurate estimation of the true contact area. And the beta parameter is something that we geometrically motivated to be this interesting quantity, approximately 0.15. Okay, to prove you that this formula works, we did some convergence tests. We simulated the same contact for different discretization from 256 by 256 up to 4000 by 4000. And you see that slowly, for finer and finer resolution, the contact area result converges to some limit values. The same rough surfaces simulated and post-treated with this formula provide us with the same result. So for all the simulations, we obtain the same master curve, which is resolution independent. And so thanks to this correction, we could obtain very accurate results. Why we need these accurate results? Yes, because in our community, in this mechanics of rough elastic solids, there was a story, long story about the effect of Hurst exponent, which is, I recall, resolution independent parameter of surface roughness, very good one, that the conduct area depends on this parameter. And here are some experimental data from different groups. And in our study, what we could demonstrate, that, so here I show you the second derivation between conduct area and normalized pressure as a function of Nayak parameter alpha. So you can see there is a slow, very weak dependence, but still there is some dependence on the results on the conduct area on the Nayak parameter. However, at the same time, what you can see for different Hurst exponent, but for the same alpha, we obtain more or less the same results. Therefore, we believe that Hurst exponent on itself doesn't affect the results, and that rather the conduct area depends on the alpha on the Nayak parameter. And so to complement this data from other researchers, we plotted our lines for different pressure value, normalized pressure value, which predicts how the conduct area should depend on the Hurst exponent, but not because it depends on the Hurst exponent, but because when we change the Hurst exponent, the alpha Nayak parameter changes as well, and it affects the results. Okay, so now we got to the first take-home message, and that first take-home message that the conduct area evolution could be with a good accuracy up to approximately 30-35% of the conduct area can be predicted by this simple equation. I can simplify even further. So the conduct area is a function of a squeezing force is given by linear term. This one is well known, and this some quadratic correction which bends the conduct area downwards. So we get a concave function. And here there is one single characteristic of material. It's E star, the only one that we need. And there are two geometrical characteristics: alpha, this Nayak parameter, it's a combination of SQ, SDQ, and SDDQ, and SDQ as it is. Okay, if you know how the conduct area evolves, we know if we use this adhesive theory of friction, we can predict also the friction coefficient evolution with applied force, which could be predicted by this simple equation. Okay, that's a good point that we can predict the conduct area. However, the bad point, the drawback of these equations is that alpha and SDQ are resolution dependent roughness characteristics, so it means that it's not easy to evaluate them properly. So if you measure your surface roughness with stylus or with AFM on small scale, you'll obtain different characteristics, and therefore you cannot really predict this alpha and SDQ. So what to do? In reality, we need to add some more physics into the problem and to include some inelastic behavior of materials. For example, add some plasticity, which would help to solve the problem and provide the evolution of the conduct area as a function of squeezing pressure. I show you some snapshots of simulation, fine Thomas simulations for loading and unloading. So here you can see residual shape on the loading with a rigid flat. However, well, I have no time for this story. Maybe next time I will present this one. Okay, now let's talk about the sealing properties of the conduct interfaces between rough surfaces. And the problem that we try to solve is the following. We will solve a Reynolds equation for incompressible fluid creeping fluid. So simply divergence of flux equal to 0, and the flux is given by a gap clearance to the power of 3 divided by viscosity times pressure gradient. Okay, very simple equations, linear problem if you know the gap field in the contact interface. Before I show you, here, before I show you simulation results, I would like to mention two approaches to this problem. The first one is when we assume that the fluid pressure is small compared to the contact interface pressure, and that we can neglect the effect of the fluid pressure on the deformation of the solid. So in this case, we will have, we are talking about static sealing, so there is no relative motion, and the pressure in the fluids are generally not that high. However, if the pressure in the fluid are comparable with the contact pressure, we need to take into account this deformation of the solids, like an elastohydrodynamic lubrication. We need to take into account the effect of the fluid on the solid. Okay, and that would impose a two-way or strong fluid-solid coupling in the interface. But let's start with the left one. And before I start with the numerical methods, I would like to show you briefly that there are analytical approaches that exist which can allow us to predict the effective transmissivity in the contact interface. So here's the equation. If we can solve this equation, whereas A prime is the contact area fraction, G is the gap, and P of G is probability density of the gap. So if you know the probability density of the gap in the contact interface, we can predict with high confidence the effective transmissivity of the interface. And if you don't want to solve the contact problem that I demonstrated just before, we can say, okay, high distribution of the surface we know, and of the other one we know as well. And so we can simply use overlap theory and say what penetrates, it's in contact. So it's kind of Winkler foundation analogy, right? What penetrates, that's in contact. What doesn't penetrate, it's out of contact. In reality, you know that it doesn't work from contact mechanics points of view, but why not to try? If so, if we use this assumption, then to know the probability density of gap, we simply need to high distribution of the surface roughness, just simply shift and cut, right? And in this way, we will obtain the high distribution, the gap distribution in the interface. My idea is to demonstrate you that it doesn't work. So what I did numerical simulations of the contact between rough surfaces, and I tried to fit this shifted high Gaussian distribution to fit with the obtained data. So you need to look at the black line. This is true probability density of the gap that was obtained from simulations, and the blue line is just shifted Gaussian curve. What I tried to fit the tail of this black line that it fits with the blue line. Okay, for the contact area fraction of 1.6%, we see the story. Okay, there is small difference near the contact for very small gaps. There is some deviation, but if you increase the contact area, you can see if I fit the tail of the distribution near the contact interface, the difference is huge, and this difference becomes huger and huger for higher contact areas. Okay, so it's just to say that simple overlap model doesn't work at all, and we cannot predict the gap distribution using simple shifting and cutting of the high distribution. All right, another argument is could be constructed on this simple rough surface. It's bisinusoidal surface. And we can use a geometrical overlap model for this one to simulate contact or to solve properly the contact problem. So I increase the force And what we get, first of all, well, not the first of all, I will focus on the conclusion. The percolation for this geometrical overlap model occurs at 50%, of course, when this contact area percolates, okay, in this chessboard pattern. However, if we solve properly the contact area, the contact problem, the percolation occurs at 40%, approximately 40%, and so it happens earlier, and nothing to do between these two figures. Okay, it was simply to say that the simple overlap model or Winkler foundation doesn't work here, and the gap distribution is considerably different if we solve this contact problem properly, and also the percolation limit is different. Okay, now let me show you what we obtained in our simulations. It's a weak coupling simulations, and first of all, we solved contact problem using the spectral method, and on the top of it, we solved the Reynolds equation for the fluid flow using the finite element method. Okay, in blue, I show you contact areas plus trapped area, trapped fluids, and in red, I show the intensity of the flux in the contact interface. So I increase the pressure, and you see that the contact area plus trapped area increases, and the flux near the percolation limit, the flux changes the channel. Okay, and near the percolation, there are a lot of area where fluid cannot happen, and there is one main channel which remains for the fluid. There is periodic boundary conditions on top, on the bottom, goes from left to right or right to left. Symmetric problem. Okay, now just 2 words about these big blue zones. In reality, I said that it contains not only the contact area, which is shown in black here, but also the trapped fluid in the interface. Trapped fluid here, we simply ignore it. We assume that that in empty space, in a vacuum, we squeeze together, and only on the later we put the fluid in the interface. So we assume that the trapped fluid doesn't affect the problem. In reality, it does, and I will show you some slides showing to which extent this trapped fluid can be important from different points of view. But already here, what we can say that the trapped fluid, these trapped legs of the lubricant or the fluid gas, they do not participate in the flux, right? In the global flux, there is no flux here. It's stuck, the fluid here. So therefore, in this effective medium analytical equation, we need to, in order of using A prime, the contact area, we need to use A prime plus area corresponding to the trapped fluid. So it needs to be changed here. A small point, but more importantly, that the trapped fluid, either gas or liquid, they will participate in the global load-bearing capacity of the interface, right? Because it will be squeezed, pressurized in these pockets, and it has to be taken into account. So, and closer we approach the percolation limit, the bigger this trapped area becomes. And yeah, the percolation, it can be very huge. So in brackets, just to mention our work with Andrei Schwarz on the trapped fluid in the contact interfaces, some very interesting results you could obtain. This problem is well known from Kuznetsov, his famous paper published in '85. So 30 years later, we could improve his results, demonstrating that for small pressure, his solution works very well. So we load the contact before we pressurize the fluid. We follow Westergaard solution. When we pressurize, we follow Kuznetsov solution. But if you try to push it harder and harder, you will see that the contact area reaching its maximal value, will start to decrease if the fluid is incompressible, and at some point it will open the interface. And of course, it will affect the static friction coefficient, and the static friction coefficient is given by these curves for different fluid volumes. So the static friction will be increasing function of the pressure. No, sorry, it's not the static friction, it's frictional force. It will be increased with the pressure, saturate, and at some point start to decrease with increasing pressure because of the trapped fluid in the contact interface. Okay, and here if we take into account not incompressible fluid, but fluid which is compressible, but in nonlinear fashion, we can have a very peculiar behavior of the global coefficient of friction normalized by the local one. So the global coefficient of friction can go up and down and increase again. So the behavior of the interface is strongly affected by the trapped fluid. Okay, getting back to my results, to our results on the transmissivity of the interfaces, I would like to highlight that if the contact area, I already mentioned, it behaves in slightly concave fashion on its concave curve. However, the effective contact area, which combines the contact area plus trapped area, it follows up to a certain limit. It follows quite nicely linear evolution with the applied pressure. Okay, these two curves. And if you look on the permeability or transmissivity of the interface, we can show that transmissivity decays as an exponential law of this effective contact area. And combining both, I won't go into detail. I will simply show you the final equation, phenomenological one, which forms actually the take-home message number 2, that the flux in the interface is given by this simple equation, which combines what's important for us, two geometrical characteristics of the surface roughness, SDQ, which I recall is resolution dependent, and SQ, which is simply RMS of roughness, the resolution independent quantity, which is important for the fluid flux. I think it's time to end. So the second take-home message, just to mention that it was one-way coupling. So we didn't take into account the fact that the fluid will exert some pressure on the interface and can change in the morphology of the contact. But we have some results with Andrei, again, recently published, where we took into account all this in a strongly coupled way, like in elastic hydrodynamic lubrication, but taking into account nonlinear compressibility of the fluids in the pockets trapped in the interface. That's it. Thank you for your attention.
Thank you, Vladislav. It was very interesting. I liked the take-home messages. Very interesting. I remind everyone to write questions in the chat. And in the meantime, I'm wondering, Vladislav, what to do with these quantities that are dependent on the measurement resolution. How to approach this, both for the contact area going to 0 and for the last equation that you showed for the fluid flow. Is there anything we can do? Let's say if I'm an engineer, what should I do?
Yeah, it probably depends on which kind of material you work with, right? And also it depends on which resolution, in which scale you work. For example, we had a project with nano-indentation, very light nano-indentation on gold surface. The size of the sample was 6 by 6 micrometer, and with AFM, and the surface was electroplated gold on silicon. And in this case, it was fine. And the surface was really clean, neat, and there was no this power spectral density that goes to atomic scale. It was smooth at the smaller scales. So in this case it worked, but in the scale it's 6 by 6 microns, so very small, not usual maybe for most of applications. But if you work with the metals, I running in will smooth out some upper peaks. It's my belief, because I don't really work in this domain, but I believe that so plasticity can help to erase some high frequency oscillations in the interface. So you get you reach some stationary roughness, and probably the stationary roughness could be characterized in a proper way using this RMS graded SDQ and so on. But well, to do so, you don't need to evaluate SDQ of the entire surface. You need to evaluate SDQ of the surface which can potentially come in contact only, because even running in procedure cannot erase the high frequency roughness in the zone which doesn't come in contact. Yeah. That's my recipe for as a not a practical engineer, but as theoretician.
Yeah. Yes, but thanks. I see there is a question from Leon Jacobs. I will unmute him. Just a second. His name, but I will read his question. How does this relate to quantifying fluid flow through two rough surfaces as presented by Patir and Chen a long time ago with the stochastic Reynolds equation?
Yes, I remember the paper, but what I remember from this paper that their notion of anisotropy in mechanical contact. That's what I remember the most. I could comment on this part, but I need to get back to the paper to comment on the results on stochastic Reynolds equation. Just to comment on this part of about anisotropy. So the idea was to have a contact interface made of elliptic contact zones, right, differently oriented, and to characterize this flow factors in the interface. And yeah, actually, the idea was not correct, because even if the surface roughness is completely isotropic, I mean, it has completely isotropic power spectral density, and you cannot distinguish any particular direction. In reality, as I demonstrated in my slides, the orientation of the ellipses in the contact interface of asperities is not at all. The asperities are not circular, and actually, the probability to find a circular asperity in the interface is zero, strictly zero from a theoretical point of view. So all asperities are elliptic and ellipsoids, and they oriented in a random way. That's what I can comment on this paper, but I don't remember the details of the results. Sorry.
Leon Jacobs, you can unmute yourself if you'd like to comment or ask something. Okay, but otherwise.
No?
Yes, Leon?
Yes. Okay, yeah. Thanks for your answer. Yeah, the nice thing about it is, of course, that it's yeah, very simple method, let's say Patir and Cheng, which can be implemented in even more analytical way of solving the Reynolds equation. So I wondered how big the differences would be, or something like that. So I think that anisotropy of the surface is taken into account via this Peclanic number. So that gives you no rotation of the surface roughness. But yeah, obviously there are some assumptions being made which can be done better, most likely. But I wonder, yeah, for let's say for the engineer, how far are you off if you're using that model instead of more, let's say, complete model as you propose it?
Yes, thank you very much for the question. And actually, maybe you can recall, because in order to solve a Reynolds equation, you need to know this gap, right? The clearance G field. What did they use in their paper?
Yeah, what they did is they modeled also with the finite element, as I understand it, and then they compared the flow through, let's say, rough surfaces. They compared it with the flow through smooth surfaces, and from that they deduced some kind of correction factors, which they call flow factors, indeed.
Yes,
And
right.
that's the way how they deal with it. And these flow factors can then be used by an engineer in a rather simple model, let's say, to solve these equations. So that's what I do in my work. So I wondered how far am I off by doing that.
Yeah, I need to check it in more detail. But actually, our approach, this final equation, that take-home message number 2, actually it kind of flow factor as well.
It's also a fit of your results. Yeah.
Yes, so you can use effective transmissivity for some representative part of the surface, at which we can assume some uniform external pressure. But well, the good thing that this equation was obtained by very accurate simulations of mechanical contact plus fluid finite element solver for the fluid in it. And the roughness constants are very similar, very simple. SDQ and SQ, that's all you need, if you can obtain them somehow.
Thank you very much for your answer and for the rest of the presentation.
Yeah, thank you, Leon.
Yes, there was an interesting question indeed. I guess in view of time, Vladislav, thank you again for the wonderful presentation. Yeah, and for the take-home messages. The recording of the seminar will be available on TriboNet, and we will send a link to everyone if someone would like to go back to the slides. And in case if you have any questions, please contact Vladislav. And I hope you guys enjoyed the seminar as I did, and I would like to thank Vladislav again for your presentation, for discussion. Thank you everyone for the participation, and I would like to wish all of you a good weekend.
Thank you very much, Aidar. Thank you, Manoj. Thank you for organization. Thank you for everybody listening, and yeah, great weekend.
Thank you. Thank you. Good luck with your further research,
Vladislav,
and we hope to see you next times as well.
Yeah, thank you. It was a pleasure.
Thank you.
Bye.
See you guys.
See you guys. Bye.